go to your presentation.
Hello, everyone. My name is Patrick Schmidt. I'm from a PhD student from the Technical University of Denmark. I'm gonna present a joint work between the Technical University of Denmark and the Center for Research and Technology of Hellas. And I'm gonna present you our work on a semantic 3D reconstruction model for concrete deposition. To give you a bit of the context, I'm also using the slides of our EU project RTAB-Map. The project aims to basically replace this shotcrete worker by 2 autonomous mobile robots. And the motivation for that is just the occupational health implications of this work. It's very tedious, it's very monotonous, and you also have the dust created by the shooted concrete that can be quite dangerous, especially for airways if no PPE is worn. But yeah, so out with the old, in with the new. So basically we have 2 robots, a shotcreting robot actually performing the work, and a inspection robot that is here, but let's just assume it's this one, which will perform an inspection and like just a mapping of the construction site and like our setup that we deal with upfront before the shotcrete robot actually does the work. So this work is mainly concerning this inspection robot, and we call this semantic 3D reconstruction. So a robot would need to know where to apply just like concrete and how much. So what we first need to do is to identify regions of interest. Now we are talking about reinforced concrete and reinforced shotcrete. So these areas where we need to apply concrete are usually, well, you can identify by identifying regions where we have exposed reinforcement bars. And after we have identified those regions of interest, we need to reconstruct a 3D model of the region of interest. And then we have a resulting semantically annotated 3D mesh that we can then use in a further step for volumetric modeling. Here is like a short diagram overview. So basically it's 2 separate components. We have a semantic understanding component, identifying those regions of interest, and a 3D reconstruction module, reconstructing a 3D model of the scene. The input to each module, like the semantic understanding module, just consumes RGB images and outputs a semantic segmentation mask. The 3D reconstruction model takes RGB images and depth images for odometry estimation and 3D reconstruction. Yes, I apologize for the GIF, it's a bit quick, but what we can see here is the output of the model. It's the output of a YOLOv8m-seg segmentation module, which we trained with a custom pre-training schedule. We trained it on a custom data set. It's a small data set, 916 images, in a very usual train, validation, and test split. What you can see here in red is actually cases where the segmentation model itself failed to provide an output. So what we did is, in each iteration where we actually have a valid output of the segmentation model, we initialize a segmentation tracking module, which is SiamMask. It's a very common mask tracking module. And that basically makes the output of the segmentation model a bit more robust. Since we are operating in a low data regimen, we wanted to use this tracking module to stabilize the output. And we saw that it boosts the MIU by 0.1. So yeah, from about 0.7 to 0.8 in MIU. And we deployed this as a ROS melodic node. The second part is the 3D reconstruction module. It is a InfiniTAM volumetric reconstruction module where we use RTAB-Map as a visual odometry module for the camera pose estimation. We used RTAB-Map because the original visual odometry estimation module of InfiniTAM was performing quite poorly. And InfiniTAM is a more modular approach to 3D reconstruction. So we exchanged the module to RTAB-Map. The sensor that we used for this setup was the roboception RC and we could see that the performance is kind of highly sensitive to the performance of the stereo camera. What we can see here is the actual 3D reconstructed mesh of the whole scene without any semantic annotations. So we can see these two wooden frames with the exposed rebars that is like our mock-up construction site. Coming to the output, it is a, as I said, semantically annotated 3D mesh. So here we can actually see the 3D mesh, but we have the regions with exposed rebar highlighted in cyan. And these are actually images from the test sequence. So the training hasn't seen these images before. All of the test beds, also the test beds that we collected data from, they feature wooden panels with exposed rebars. In this specific case, it's a 2 meter wide and 1 meter tall panel. And these dimensions are then used to evaluate the performance of the 3D reconstruction method. So we took 12 point-to-point measurements to evaluate the root mean squared error of the 3D reconstruction, and it's boiled down to 0.564 centimeters. For the semantic segmentation module, the metrics can be seen here. So we achieve an MIU of 0.85, a mean precision of 0.96, and a mean recall of 0.88. Yep. That's all, and thanks for listening.